Okay, so section 11.1 today. Share the screen. Here it is. Okay, so here's what I've got planned for us. We're going to finish chapter 7 pretty much today, unless you have some more questions on Friday. But we're not going to take the test until Wednesday of next week. Okay, so if you, sometime between now and Wednesday, you have to find a way to get connected to the Zoom meeting with video. Okay, so if your video's been working and you just had it turned off, great. You have to turn it on. I got to proctor you. I got to watch you while you take the test. If you, if you don't have one on your computer, then you're certainly welcome to just use a phone. That works pretty good, right? I was, watching Elton John's concert, and they seem to be able to sing on their phone without any trouble. So you guys should be able to do a little math on your phone without too much trouble. It doesn't have to be a high res or anything. You can just set your phone like on the table next to you, and that way I can say, yes, my guys were all proctored and it's all good, and we have test reliability and all that kind of good stuff. And I think that's better for you, because I don't want people to come back and say, well, that virus semester, those kids should have to go take those classes again because they didn't really learn anything, right? And I want to be able to say, nope, they really did learn something I watched, okay? So, just for our own sanity and our own protection, I guess, I don't know, I would like to be able to watch you while you take your test and proctor. So sometime between now and next Wednesday, get that figured out. And then we're just going to sign in at the regular time, 8:30, do the test. And then if you need a little extra time, most of it, well, it's going to be the same. You can either write on it electronically or with a pencil, and then take pictures of it and upload it back to me. And if you need a little extra time to do the uploading, we can do that too. Won't be any problem. Katie.
I'm sorry. I was thinking in my head.
Okay.
I was imagining a line.
Okay. Thought you had a question. Any other questions?
So it looked like there was 2 parts to the test. How long will the first part be?
Shorter, enough that you can do it in an hour. And, so what I did is I did some integrals that I think you should be able to do kind of in a timed environment with, given enough time. And then I put half of them on a take home, although now technically it's all at home, right? But a non-proctored section where you can, spend the rest of the evening or as much time as you need doing a few more. Okay.
What will be the time limit on this part 2?
Oh, I think part 2? No, part 2 you'll have I don't know, all day. I don't know what I put it. I think I put it till midnight.
Okay.
So plenty of time to do the take-home part. The in-class part, I was planning to be here for a couple hours, but I think it might take you 45 minutes. So time shouldn't be an issue on the first part.
And then last question on part 1. Will it be released at 8:30, or will it be released a little bit before so we can get it printed off and ready to go?
Oh, that's a good question. I was planning to release it at 8:30 when we first got here, just so that I would be here in case you had problems. But again, I don't think it's going to be a time issue, right? If at the end you need a little extra time just to get it processed and uploaded, we'll work that out. But I don't think you will. Okay, so that's Wednesday of next week. That'll be the test. And then we're going to get started on chapter 11. Chapter 11 is going to be our very last chapter, but it's a long one. There's about actually 11 sections. We're going to break it apart into a test after about 7 sections, I think, and then a big quiz for the last little bit. So we're going to have the chapter 7 test, basically the chapter 11 first part test, a big quiz for the second little part of chapter 11 and the final, and then we're done. So chapter 11 will be our last chapter that we're going to do, and we're going to get started today. So that's the calendar. What's going on here? Oh, I see.
Will the final be in the same format as a chapter test?
Yes, well, more or less. I'm leaning toward making the final exam, putting the final exam in Canvas. In the past, what I've done is I've used sort of a multiple choice format where you can then also show your work. And so what I'm thinking is that I'll put the final in Canvas. You'll be able to select, multiple choice answers and then write on paper your justification if you want to provide supporting justification, and then upload that to me, and I'll look at your work for partial credit, and we'll just, and then the test will be in Canvas, so it should be easier to administrate. And that's what I was planning for the final. We're going to do at least right now, the plan is to do the final exam on the same day that it was going to be scheduled for. So I think that's, for us, I think that's Wednesday of finals week. And we're just going to go at the regular final exam time. But maybe I told you this before, because we're on that weird 8:25 start time. Originally, our final exam was scheduled from 8 to 10. And so let me get word from the school about whether they want to provide some flexibility of the time or if they want us to do it exactly at the scheduled time. But we're either going to start at 8 and go to 10, or maybe 8 to 10:30, so that there's a little room for you to do some uploading. Or we'll start at 8:30 at the regular class time and go to 11. Okay, but it's going to be during finals week. That'll be our last test. And of course, I'll have more information for you as we get closer. Any more questions about administrative stuff, calendar, tests, what's going to happen? We may have to make some more changes as we go down the road, right? But right now, that's my best guess at where we're going. And I will certainly keep you posted and updated, if things change. Okay, so here you go. Here are the last few questions from chapter 7. These are all what we would call improper integrals. And the first one, obviously improper. You can't plug in a minus infinity. So that's screaming out to you that you need to do a limit. And then in 2 and 3, it's a little bit more disguised. Maybe not so much in number 2, right? There's a problem plugging in 1, be dividing by 0. Can't divide by 0, so it's undefined. So what we want to do is take the limit as I get close to 1. Okay, and then in number 3, depending on, how comfortable you are with domain and range, you can't plug a 0 into the natural log function, because again, that goes to minus infinity. And so all these fall into the improper integral category. To do them, we have to find the indefinite integral and then go ahead and plug in the limits of integration and take the limit on the ones that happen to be going, somewhere infinite. So it looks something like this. You have to first find the antiderivative of x e to the x. Then you're going to plug in these limits and evaluate, plug in the limits of integration and evaluate the limit. Okay, so since this is looking like a product, I'm kind of feeling like parts. So I'm going to do something like this. U is x, dv is e to the x dx, du would be dx, v would be e to the x. And I'm kind of thinking that maybe some of these you're starting to recognize. But if you're going to use parts to get it, you don't have to show every single step, but I would like to see on your work that you used parts, right? Or you could say, I used parts, or you could say, I would have used parts, but I have this one memorized. Okay, that's fine too. So we get x e to the x minus the integral of v du. So notice that now we have to put the limits of integration on here. So some people like to do the indefinite integral first, then substitute the answer back in. Some people like to keep the work as we go. And if you do, then you should probably write something more like this. This is from minus infinity to 0. This is the integral minus infinity to 0 of e to the x dx. Some people like to evaluate parts of it as they go. Some people like to plug in and evaluate at the very end. Again, that's up to you, but you should, if you're kind of sharing your work, be organized enough that you don't confuse yourself, okay, about what you did. So here I'm going to plug in. 0 goes in here. 0 would be 0 times e to the 0, which is 1. 0 times 1 is 0, so I get nothing. And now I can't plug in this minus infinity, so I'm going to write this as the limit as t goes to minus infinity of t e to the t. Okay, except I messed it up, didn't I? Because when I plug in 0, I get the 0, and when I plug in the minus infinity, it's supposed to be subtract. So now I think that looks better. Okay, what do we got over here? We got minus the limit as t goes to minus infinity. The antiderivative e to the x is e to the x, right? So what do we have? We've got e to the x from t to 0. So doing this one, maybe we'll do all the limits at the end. So t goes to minus infinity. I got minus t e to the t. Over here, I've got the limit as t goes to minus infinity. Plugging in 0, e to the 0 is 1, and e to the t is e to the t. So all that remains is to find these limits. So now we're back to, I don't know where we are. When did we do this? Like October, maybe. And so I'm looking at this and I'm saying, uh-oh, if I plug in minus infinity here, this goes to infinity, and then e to the minus infinity. Well, let's see. E to the negative is 1 over e to the infinity. E to the infinity gets really big, so this must be going to 0. So this is going to infinity, and this is going to 0. Sounds like an improper form, or maybe an not improper, indefinite form. What did we call that way back there? Do you remember? I don't remember, but what I'm thinking is we had to use a trick to this. It's going to matter who's going faster. Either this is going to infinity faster or this is going to 0 faster. So if this one's going faster, it wins and this goes to infinity. And if this is going to 0 faster than this, then it wins, and 0 times anything, of course, would be 0. So do you remember how we resolved this? Nobody remembers. Guy's name was L'Hopital, right? This is L'Hopital's rule. We said, if we want to compare how fast these are going, we want to take a look at their rates of change. But L'Hopital's rule only worked for indeterminate forms of 0 over 0 or infinity over infinity, not infinity times 0. So we have to do some more work on this, clean it up, and write it this way. The limit as t goes to minus infinity. And so what we're going to put in here is we're going to leave this e to the t in the numerator and put 1 over t in the denominator. Because now when I put in minus infinity, this top goes to 0. And then when I put infinity, minus infinity in the bottom, 1 divided by something really big goes to 0. So now this thing is an indeterminate form, 0 over 0. So here's what we wrote. We wrote equals, do I remember writing 0 over 0 in here for indeterminate forms? It's a warning to your reader that you're going to use L'Hopital's rule now. So then you say, take the derivative. So I say the limit, t goes to minus infinity. The derivative e to the t. The derivative of 1 over t minus 1 over t squared I'm feeling like this isn't looking so good. Because I'm feeling like that is still going to 0 over 0. Are you with me? So our change here wasn't the right change. So what do we have to do? We have to go back and consider this again. So here's what I'm going to do. I'm going to skip down here. Let's not forget that we still have this part to do. We haven't done this part yet. All right, so I'm coming down here and I'm saying the limit as t goes to, this whole minus thing is bothering me. So what I'm going to do is switch it around. Instead of going to minus infinity, I'm going to go to positive infinity. So that would make this t positive, right? And this t negative. So changing it by multiplying by -1, I have this limit. I think this is going to be easier for me to see because that limit is the same as t on the top and e to the t on the bottom because of the negative exponent. Now the top goes to infinity and the bottom goes to infinity. So we have the indeterminate form infinity over infinity. So we can use L'Hopital's rule and get the limit as t goes to infinity of the derivative of t, which is 1, and the derivative of e to the t, which is e to the t. Now, as t goes to infinity, the bottom goes to infinity. The top is 1. So 1 divided by something really big sounds like about what?
0.
That one goes to 0. Okay, awesome. So we go back up here and we say this part, right? That part goes to 0. So now we have this part in the box still to do. So I'm going to write it down here at the bottom, and I'm going to put the minus on the inside. So I'm going to say the limit as t goes to minus infinity of e to the t minus 1, right? So there it is there. I put this minus right here on the inside so I don't forget about it. And so what happens when it goes to minus infinity? Again, if the minus is bothering you, like it did in the other half, you can make this go to infinity, in which case this goes to e to the minus t minus 1, right? But e to the minus t, right, is 1 over e to the t. And so now as t goes to infinity, the bottom gets really big. This part here goes to 0. -1 goes to -1 because it doesn't have a t in it. And I think we get -1. So the first half, this part here went to 0. So we get 0, and this part goes to -1. So the whole thing goes to -1. So guess what the answer is? -1. And we're done. Although this was a whole big long problem, and we had to remember L'Hopital, and then we had to apply L'Hopital correctly to find the limit. This seems pretty involved to me, which is why you shouldn't be worrying about studying for the comprehensive final exam, because like every test is cumulative, isn't it? I mean, we got to remember everything we've ever learned in any math class ever to be able to do the next step. But one thing that I might want to do here is check, because the problem kind of took a long time. It was our first one. It was a little bit messy. So let me go ahead and share the screen and put this up here.
I've actually got a question about that too.
Okay.
If we're finding area, why would it be -1?
That is a very good question. Let's take a look at Desmos and see if Desmos can help answer that. What is going on? My little window, oh, there it goes. Okay, couldn't get my window with all of you out of the way. All right, so Desmos. here we go. So let's put it in and find out what we got. So we want f of x is equal to x e to the x. Okay, so there is our curve. And we want the area, right? We want the area from t to 0 of f of x dx, where t gets really small. Yeah, something like this, up to 0. Okay, so t is going to start here and it's going to get smaller and smaller. Oh boy, it got small real fast. Okay, maybe that's too big. Minus there, 100. Okay, so what happens? We're finding this area right in here. Notice where the area is. It's under the axis. So that means if you were measuring the height would be negative. Making sense? So the area isn't really a negative area, but it's a signed area. So the sign on this area is going to end up being negative because I'm below the axis. So it does make sense that we should get a negative value for the area. And then the question is, how much area is in here? And to be able to answer that, we got to know, well, that's going to kind of depend on how quickly this red line is squeezing off the area. In other words, how quickly it's getting close to the axis. We know that if this gets close kind of slowly, that it doesn't pinch this off well enough and the area ends up being infinite. But if it's getting closer faster, then essentially it almost like it's the distance between the curve and the axis is getting small, right? So quickly that the area that we're adding is growing at a much, much lower rate. Okay, and so it's kind of a race, just like L'Hopital's rule. Am I adding area faster or am I squeezing off this distance faster? Okay, and it turns out that if you squeeze it off fast enough, we actually get a finite value for the area. So how do we know if this is squeezing this off? We do all that limit stuff that we just did, right? It's just like the finding the limit using L'Hopital. So how much is in here? I don't know. This looks like about 3 long over to there. So that's 3. And this looks like it's about 1/3 of the way down. So 1/3 times 3. That looks like it's about 1 in this part. So I wouldn't be too surprised if we got an answer somewhere around 1. And so you can just slide t over, check it out. By the time we get to 11, we're getting pretty close to 1. And then by the time we get to, I don't know, somewhere right in here around 30, huh? Around 30, Desmos runs out of decimals. And I'm kind of thinking that Desmos is suggesting that this is going to go to -1. Okay, remember that -1 isn't really a -1, right? It's just that Desmos is rounding it off because it doesn't have any more decimal places. But we know better. We know it really is -1 because we evaluated the limit. And so you can always use sort of Desmos to check and see what's going on. Okay, questions about that one? Okay, maybe this is going to be a little longer than a warm-up. I don't know. These are hard. All right, let's try the next one. Integral 1 to 3 of 1 over x minus 1 dx. So this one is a little tricky because you can find the antiderivative, right? But then you have to be careful about plugging in, okay? Because you can't plug in this 1. So what do you really want to do? You really want to write this as the limit as t goes to 1 from the positive side of the integral of t to 3 of 1 over x minus 1 dx. Okay, and so let's do that. the limit as t goes to 1 from the plus side, we get the antiderivative of 1 over x minus 1. Hopefully that one's a little bit easier. Yeah? What is it?
Natural log of x minus 1.
That's the natural log of the x minus 1, isn't it? From t to 3. So then we say equals the limit t goes to 1 from the positive side. Putting in 3, we get natural log 2, right? And then we get minus the natural log of t minus 1. So then we say, what happens? Okay, so log 2, well, that just goes to the natural log of 2, right? That's about 0.683 or something. And then what happens when I put a 1 in here? That means I'm going to the log of 0, right? It's definitely positive, so I'm going from the positive side. So then we say, well, what is that? Well, what's log do when we get close to 0?
Goes to negative infinity.
Goes to negative infinity. Here's the log right here, right? So if you can remember the graph of the log, you just sketch it like that. If you can't, go look on Desmos. So this looks like it's going to negative infinity. So negative infinity sounds like infinity. And infinity plus 0.683 sounds like infinity. So this whole thing sounds like it's going to infinity. So then what? You say, does not exist, right? Or you could say diverges. Mostly we would say diverges. Okay, the limit does not exist, so the integral diverges, meaning that it grows faster and faster and faster. Okay, so let's take a look. Here it is again. If I can get this back up here. I wish there was an easier way to share. Switching back and forth, that'd be nice. Okay, 1 over x minus 1, and we want to know what's happening from t to 3 as t gets close to 1. So we need to get close to 1 this time. So let's say 1, I don't know, 2 or something like that. And then we can get close to 1. Yeah, so we can get close to 1 as we come down here. And you're saying, 3.5, 3. Maybe you put something really close to 1 in here. Oops, that's too close. Right? 12, 14, 16, 19. How come it's undefined? Not enough decimal places in Desmos. So it looks to me like it's growing bigger and bigger. And if we look at the graph, then we would say, yeah, 3, it's bounded. But as I get closer to 1, I've got an asymptote. So if you want to put it in there, you can say x equals 1. You know, and if you want to make it pretty, you can make it dotted in red so it's in there real nice. And so what we're saying is, look, there's a gap, right? There's a gap up here. And it's not getting pinched off fast enough. So we're adding area faster than we're closing the gap, which means the area just keeps getting bigger and bigger and bigger and bigger, goes to infinity. We say that the integral diverges. Questions? That one was a little faster because we didn't need to use integration by parts, and we didn't need to use L'Hopital's rule to evaluate the limit, right? That was just kind of a, do I understand what's going on with the problem kind of thing. Okay, so one more. The natural log from 0 to 1. So you should, maybe since we're right here, we can say natural log, and then we can say 0 to 1. The problem's going to be at 0, so we're going to say t's got to get closer to 0, right? And we would say something like this. We don't need an asymptote. Or we could have an asymptote if we want. X equals 0. And we'll make it pretty again. Okay, there we go. So now what's happening? This is the area in here, right, in this little sliver. So we're going to get a negative number if there is one. But look at what's happening. This is getting closer and closer to the asymptote. In fact, in this case, it looks like it's getting closer faster than in the last example. So are we sort of closing this gap faster, or are we adding area faster? Which one? And in this case, we're closing the gap faster. No, I don't know. I guess we're going to have to find out. We haven't done it yet, right? But if you get a number, what's it going to be? Well, I don't know. This looks like a rectangle 1 by 3, right? That's 1 by 3. So that's an area of 3. If I were to cut it straight across here, I would get half of 3. So that's like 1.5. So if I got something a little smaller than 1.5, maybe even 1, somewhere around -1, I'd be feeling like that might be reasonable. Okay, so how do we do it? All right, we try to anti-differentiate the log. Uh-oh. You guys remember how to anti-differentiate the log? While you're thinking, I'll rewrite.
Integration by parts.
That's integration by parts. Or you could do what?
Have it memorized.
Just memorize it. Why don't you put it on the list of those 20 that you have memorized and just write it down? That'd be way faster. So which is it? You got it memorized?
X ln of x minus x.
That's what it is. It's x log x minus x. I will let you guys do integration by parts if you don't have it memorized. Okay, so I plug in the 1. The log of 1 is 0. Here's our log graph up here, right? So there's 0 right there. So what do I get? I get 1 times 0, which is 0 minus 1. So I get -1 for that part. And then I plug in the t, and I get minus t log t minus a minus plus t. Still okay? So now we have to evaluate this limit. Well, the limit of the sum and difference is the sum and the difference of the limits. And the limit of t as t goes to 0, well, this part goes to 0. So we should be okay with that part. I don't know if this is like official notation or not, but it's easier for me if I kind of do it a little piece at a time and kind of keep track. So I like to just say, okay, I dealt with this. That went to 0. Okay. And so what's this doing? That's the only question. So this is going to -1. Okay, and then we get minus the limit as t goes to 0 from the plus side of t log t. So what's the issue? Well, t goes to 0 and the log of t goes to -infinity. So this is a 0 minus infinity one, and it's a race again. So we got to use L'Hopital's rule. But L'Hopital's rule only works if it's 0 over 0 or infinity over infinity. So we want to change this around so that it's in one of those forms. So let's write it like this. The limit, t goes to 0, the plus side. Log t, that goes to infinity. And if I put this as 1 over t, well, then when t goes to 0, the bottom would go to infinity. And now I have it in the infinity over infinity form. Okay, so this is equal to -1 minus, okay, so then we use L'Hopital. So maybe we write infinity over infinity because we're about to use L'Hopital's rule. We say limit t goes to 0 from the plus. Take the derivative of the log, 1 over t. Take the derivative of 1 over t, or t to the -1. We get -1 over t squared. But now that we can use a little algebra to clean this up, that's equal to -1 minus the limit as t goes to 0, the plus side. Invert and multiply. So now I've got a t squared on the top with a t on the bottom. The t's cancel. And I end up with minus t, I think. So what happens? Well, t is going to 0. So when t goes to 0, this goes to 0. So a negative 0 is 0. So this whole thing goes to -1. And if we remember back from our picture in Desmos, it looked pretty reasonable that it would be close to -1. I mean, we kind of estimated it at -1.5 or a little smaller than -1.5. And -1 seems like a pretty reasonable guess. So the answer here is that that our curve is getting closer to the axis, right? It's squeezing, it's pinching off this area faster than the area is growing. And so we end up with a finite value for this area, even though our region is unbounded, right? And this is a weird idea. The fact that we can have a finite value for the area, even though the region that we're looking at isn't bounded. And that's really kind of a cool thing. That turns out to be sort of a big piece of mathematics that we're just kind of getting started on, and we're going to explore a little bit more in chapter 11. Okay, that was the warm-up. Okay, that took like 40 minutes. It's a 40-minute warm-up. I mean, these are going to take a little while. You're in Calc 2 now, and you're almost at the end. Notice that it draws on a lot of math, right? It's kind of one of my favorite classes in a way, because it's, when am I ever going to use this? And the answer is like right now. Right? This is it. If you don't use L'Hopital's rule today, you probably never use it again, or maybe if you take some more math, right? But after this, you know, people don't just walk around on the street and use L'Hopital's rule. You know, this is the time. And then when are you going to use a fraction divided by a fraction, right? When are you going to use this? Rational polynomials. Well, we learned that way back in Math 120 probably, right? And this is when you're going to use it, today, right? So I really like this because you get to, you know, you get to use all that math that you took the time to learn. But it does make the problems really long, right? And so just go carefully, you know, take your time, check your work, look on Desmos, make sure things are reasonable. And what I'll do to help is I'm going to give you a few that you're going to do sort of in a time, sort of proctored way. And then I'll just give you a bunch that you can do at home where you don't have to stress about the time limit. Okay, and so we're going to try to take time out of the equation as best we can. But realize that in real life, there's still a bit of a time constraint. I mean, if you're engineering something for Boeing and they need an answer to, you know, what is this thing going to look like, or how should we build it? You can, you know, be a couple days late, maybe even a couple months late. But if you have cost and time overruns like a year long, they're not going to give you another contract. So, you know, there's never a time when you're going to have to do an integral in 40 minutes. Right? But there is, you know, there is an expectation that you would be able to do it eventually, and that eventuality would be sort of a reasonable amount of time. Okay, questions? Ready to change gears? Something new? Okay, last big idea. Although this stuff that we're talking about in 7-8 is going to kind of lead us into where we're going. But right now we're changing gears to some brand new stuff. So this is officially now chapter 11. Okay, and it's called Sequences and Series. And I'm kind of surprised it didn't happen, although it's probably a little bit too far away from me. This is about the time that my phone starts talking to me out of my pocket, because it's really, and it does it all the time. I'm surprised it didn't do it. It's laying over on the counter. All right, so sequences and series. And I got some notes to share with you somewhere. I don't know where I put them. Oh, here's some. Here's some notes. Here's my calendar, and here's some notes. Okay, so I'm thinking that depending on how much and what and who you had for pre-calc, that you may have heard a little bit about sequences and series already. And so we're going to try to get everybody up to speed to the same place. But maybe some of this will be a review for you. That's fine. Just enjoy it, and we'll all get to the same place eventually. So we're going to start out with sequences. We'll talk about them today, and maybe we'll talk about series a little bit on Friday. A sequence, right? Q-U-E-N, sequence. Boy, I can't write any better on paper than I could on the board. Okay, a sequence. It is a list of numbers in order. That's it. Pretty simple stuff. It's a list of numbers in order. What if we leave off the in order? Do you know what a list of numbers not in order is called?
Would that be a series?
Close, but no. A list of numbers we call a set. Okay, so a set is a list of numbers. So a sequence is an ordered set of numbers. So the way we usually write this down is we use this little curly bracket to say, hey, I'm starting my set of numbers, right? And I'm going to put them in here like this. So how do you know if that's a set or a sequence? And the answer is you have to sort of use context. A set of numbers is the numbers 1, 2, 3, 4, and it doesn't make any difference what order they come in. Okay, a sequence of numbers is the set of numbers 1, 2, 3, 4, and they're in order, 1, 2, 3, 4. So 1 came first and 4 came last. Making sense so far? We are going to play with sequences of numbers and learn everything we can about them. So that is our plan. So give me one. Give me some nice sequence. Sometimes with sequences, we get a little lazy too, and we don't add the brackets. So we could just say, here's a nice sequence of numbers. Right? 2, 4, 6, 8. It sort of begs the question, if I wanted to look at these and, I don't know, describe them, you could say, well, all right, looks like they're all even numbers. In fact, they're the first 4 even numbers. Sometimes a sequence can be defined by a formula. Or a function. If we say a formula for the nth term. Okay, because in this particular list, it's a finite list. It just goes to 8 and stops. But we're interested in maybe some infinite sequences. An infinite sequence would look like this. Where we put the ... to say, and this list continues. It continues indefinitely. Okay, so this would be called an infinite sequence. This top one would be a finite sequence. And we're going to be interested in the infinite kind. And we're going to be wondering, if there's a ... where does this go? And how would I describe the ones that follow the 8? Okay, so there's a couple ways we can do that. First, we can give a formula for it. So you could say, all right, here's how I get the first one. Here's how I get the second one. Here's how I get the third one. Here's how I get the fourth one. What if I wanted the nth one? Right? What would that be? And if you could give a formula for that, then you would have described the whole sequence of numbers. So how about that? The first step in figuring out a formula is just figuring out the pattern. So once you have to sort of discover the pattern before you can write a rule for the pattern. And so the first question is, I've got this sequence, I've got a dot, dot, dot. What are the next three terms? And so what are the next three terms? You say what?
10, 12, 14.
10, 12, 14. Of course, this is just a guess. I mean, you don't know what I was thinking, but this seems like the most logical thing. The next three terms could have been 0, 0, 0. Okay, I mean, there's no rule for it. There's the rule. Write down, here's my rule. Write down the first four even numbers and then put zeros after that forever. That could be a perfectly okay sequence. Okay, but it doesn't really sort of follow the pattern. So when I write dot, 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 I'm suggesting that there is a pattern and you have to guess what I'm thinking. And so you have to sort of guess the most logical thing, but there's no, when I put dot, 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 it doesn't guarantee that the next are 10, 12, 14, right? The next could have been 0, 0, 0. Okay, or maybe they would have been 6, 4, 2, because maybe this sequence goes 2, 4, 6, 8, 6, 4, 2, 4, 6, 8, 6, 4, 2, 4, 6, 8, and just goes up and down and up and down. The problem with the dot, dot, dot is that we don't really know what's coming next. And you have to end up sort of guessing. Okay, but if we have a rule, then it's well defined. And then everybody agrees that, if we follow the rule, we got it. So can you come up with a rule for how to make these? Here's what you get to start with. You've got to find a rule that connects, maybe in a table form it would be better, n and a sub n. We generally use a for the name of the rule instead of f, right? F for functions whose domain is real numbers, and a for functions whose domain is the positive integers or the counting numbers. So you've got 1, 2, 3, 4, 5, 6, 7, 8, and we've got 2, 4, 6, 8, 10, 12, etc. And my question is, if I give you the n, can you give me a rule for finding a sub n? And you say, yeah, that's easy. What is it?
2n.
2n. You just double whatever the input is. So now if I want the 20th term, it's 40. If I want the millionth term, right, it's 2 million. And so now you can figure out what all of them are. So now the dot, dot, dot isn't a guess anymore. It's formally defined using this rule. Notice that this is a function. We could have written it a sub n, and sometimes we write a sub n. In other words, plug in the n to the a formula and calculate the value of a sub n. But these n's, now we might ask, so what's the domain and what's the range? And the important part of a sequence is what's the domain? So what is the domain? In other words, what numbers can I plug in?
1 to infinity.
1, yeah, this, right? 1, 2, 3, 4. We have a name for these numbers. Do you remember what we call them?
It's the natural.
Those are called the natural numbers. So we would write that as this kind of double struck n, natural numbers. For a while now, we've been working with functions whose domain is all real numbers, right? So we would have written something like f of x equals 2x. And that it implies that x is an element of the reals. In other words, you can plug in any real number to this. So you can double any real number. But we're not interested now in plugging in a half or a third or pi, okay, or -1. The only things we're plugging in now are the natural numbers. 1, 2, 3, 4, 5, 6, that's it. Okay, so it's like a subset, if you will, of this function. It's just the dots. So if we wanted to make a graph of this, it would look something like this. We would plug in 1, right? So here's 1, and we would get 2, and you put a dot there. And then you plug in 2, and we get 4, and you put a dot there. And you would keep going. So the graph of a sequence looks like a bunch of dots. And unlike most of your other classes and training, we don't connect the dots because there's nothing in between. The domain is just the natural numbers. So let's say we can do that. We can do that in Desmos, of course. But it takes a little working because Desmos is assuming that you're going to be working with the real numbers, right? Because that's what we do in most of our classes. And you already know that Desmos anticipates what you want, right? It anticipates what you want. So if you say f of x equals 2x, it thinks you want this whole line plugging in all the real numbers on this real number line. Okay, if you say f of a of n equals 2n, it just thinks that you're using, what's going on with my screen there? I don't know what's going on there. It thinks that you're still using all the real numbers and it fills in the whole line. So if you want to just plug in integers only, positive integers only, the natural numbers, you're going to have to tell it only plug in natural numbers. Okay, and the way you do that is you make a list. So all the values that you're putting in, I like using a big N, is going to be a list of numbers from 1 to as big as you want this to be. Okay, and of course, you can't put infinity here. If you wanted all the natural numbers, you put infinity, but Desmos is going to run out of decimals. So we usually just put in something big. Okay, so in other words, I just defined capital N to be a list of numbers, a sequence of numbers, 1, 2, 3, 4, 5, 6, all the way to 1,000. And then if we want to graph A of big N, then what we have is A of big N is a 1,000 element list, and that this list, okay, this list is what you would get if you plugged in 1, then plugged in 2, then plugged in 3, then plugged in 4. But instead of graphing the line, what we want to graph are the points. So to graph a point, like graph the point 1, 2, you would just put 1, 2 in. But to graph this list, we'd put N and then A of N. And then check it out. There are all of our points going off to 1,000. So now we don't have a graph that's all connected. In fact, it's just made up of the points themselves. So I'm thinking this is all fine and dandy until you want to do calculus. Why would you be a little bit concerned about thinking about this particular function in a calculus class?
Because there's no slope, and if there's no slope, there's no derivative.
There's no slope, there's no derivative. I mean, there's kind of like, you're kind of seeing the dots are following the line, aren't they? But at each individual dot, how would you put a tangent on there? You can't put a tangent on there. In fact, we know that the only functions that we know that for a function to be differentiable, it's got to be continuous. And this particular function isn't continuous anywhere. It's only made up of individual dots. So we're not going to be able to take the derivative. So we're going to have to think about things a little bit different. And notice that if I wanted to find the area under the curve, well, how would I do that? There's no curve in here. So the area under the curve with the integral doesn't make any sense. So we're going to talk about sequences, but then I'm wondering, well, why are we doing that? Because what's the connection to the calculus? In other words, you're studying this in a calculus class, so there must be some calculus connection going on. Or are we just doing a new math idea, right? And just now we're just shifting gears. Calculus is done, and now we're going to consider something brand new. Okay. I think at first it's going to feel like something brand new for a little while. And but I have a feeling that somewhere down the road, we're going to tie this back to the calculus and you're going to see what's going on. For certain, our function, right, our dots are certainly following our continuous function, 2x, if you will. Right? So the dots are certainly following that line, but when we graph a sequence, we only get the dots, that's it. So check this out. You guys have a lot of experience starting with a line and writing the equation of the line. And now what I want you to do is start with a sequence and give me the formula for it. So one of the tricks you can use is you can say, well, these dots are following the line. If I could write the equation for the line, I could write the equation for the dots. Okay, beautiful. That's a nice trick. All right, so let's go back and try some other sequences. So let's see. Here's a nice sequence. I seem to remember doing these. Did I do these with you guys, or was that just, and has that been so long ago now I'm confused? Did we do sequences together or not?
Not that I remember.
Nobody's
We
Nobody's
touched on
saying-
it briefly.
Okay. Well, then that's okay. So here's the next thing that we do. We say something like this. And I get a little lazy. I usually leave these brackets off, right? Because I don't know, they don't add too much. So here is my set of numbers in order. And the big question is, what are the next three terms? And then what's a formula for the nth term? So you'd have to tell me, what are the next three terms? So what do you think? Maybe I went too fast. I mean, we went from even numbers, which is a pretty easy pattern to recognize, to some kind of fractions that seem to be alternating in sign, right? So there are a lot of problems sort of in between there that get kind of, a little bit more difficult, right? Until you get a little practice. So there's going to be a bunch of these in the homework for you to practice on.
Okay, so it looks like we've got 5 to a power in the bottom.
Okay. That's looking like it to me. And then top?
And top. The only thing that's tripping me up with the top is how you're getting the negative switching.
Okay, so what would the next term be? Or what do you think? What do you want to guess?
Be 7 over 5 to, it's like 5 to the 5th.
Yeah, to the 5th.
So 3,125.
Yeah, exactly. And so just a little bit like statistics class, that's just going to turn into a really big number real fast. So if you write 3,125, you probably don't recognize it. I'm guessing that if I write 25 and 125, you probably do recognize those as being, 5 squared and 5 cubed. Okay, but pretty soon you're not going to, it's just going to be a great big number down here. So hopefully you'll see the pattern before it gets too big. All right, what's the next one?
-8 over 5 to the 6th.
-8 over 5 to the 6th, 9 over 5 to the 7th. Okay, I'd say that's a reasonable pattern to guess. Remember that the ... means that this follows a pattern, but you don't know what it is until we explicitly write it down. I mean, the next one could be something else weird, not following this pattern. Okay, but we're hoping that it does follow the pattern. All right, so how would we get this? It seems to me like you need powers in the bottom, right? So what we're doing is trying to write a rule. I give you 1, 2, 3, 4, 5, 6, 7. You give me these values, right?
Yeah.
So if I give you a 3, you got to make this out of it. If I give you a 4, you got to make this out of it. So what's the rule?
Looks like it's n plus 2
N plus 2.
on the top, and then in the bottom, it's -5 to the -n.
It's already in the
Oh
bottom.
no, in the bottom is n. It's just in.
I
Just
think
gonna be
that's
n.
it.
Yeah, that's it.
Yep, I think that's it. How would you know? Your rule has to work for the first 4 that I gave you and the 3 that you guessed. And then we'll assume that it keeps working for all the rest. And that's what the ... means. Now we can write
Oh
this. Is that it? I think that's it.
no,
No.
yeah, that is it. That is
Oh,
the.
no, that's not quite it. Check this out. What do we put in first? 1, right? So A1 would be 1 plus 2 minus 5 to the 1 power. So that looks to me like that looks like negative 3/5. And we wanted positive 3/5. So can we fix this up?
Do we put a negative on the outside? No,
That's certainly a way to do it. You could take the opposite of what this is. That would make this one positive, wouldn't it? That certainly works.
Yeah.
And now we got it. Okay, so now what do we do? We might want to clean this up because some people don't like this negative and negative.
Yeah,
So check this out. I got n plus 2. I got minus 1 times minus 5 to the nth power, right? Which is the same, I think, as n plus 2 over minus 1 to the nth, right? And then 5 to the nth. Is this true?
Yeah.
That's still true. You could write it like that. So is this easier than that? I don't know. Maybe, maybe not. You could write it like this. N plus 2. This is, that's one of these. So that would be 5 to the nth power, right? Let's put the minus 1 first. So this is minus 1 to the n plus first power, right? Times 5 to the nth power. We could write it that way. So any of these ways of writing it down are okay. I sort of like your first way. In fact, I might come back here and I might just put the minus up here on top like this and say 5, sorry. Well, I don't know. I don't know how I like that. I don't know. It doesn't make any difference. I'm saying that just like any algebraic expression, you can write it a whole bunch of different ways. And how do you know which way to write it? Well, you write it whichever way is the simplest for you, for whatever's coming next. Okay. And if WebAssign doesn't like the way you wrote it, then change it into an equivalent form and try that. That making sense? I don't like any of these other ways that we simplified. I kind of like this way the best, actually, now that I look at it.
Well, you could put the negative just to the left of the fraction.
Here in the front, right here.
Yeah, right there.
And that might make it look even a little bit easier. Yeah, I agree.
Yeah, it might look a little better.
Like a negative right there.
Yeah.
Okay. Okay, beautiful. You got it. Here's how the book wrote this one. They wrote A sub n, which, by the way, is the same as A of n, right? Is going to be, they wrote minus 1 to the n plus 1 power times n plus 2 over 5 to the n. So they dealt with the n plus 2 over 5 to the n first, and then they used this little minus 1 to the n plus 1 to alternate the signs. Check it out. When n is 1, you get minus 1 squared and it's positive. When n is 2, you get 3, the third power, so it'd be negative. The fourth power would be positive. So positive, negative, positive, negative, positive, negative. So this is one way that you might see it written down. And those two are going to end up being the same. Okay, so that's the game. That's how the game works. I give you a list of numbers, you give me a rule, right? That's how it works. And I don't have too many more written down here for you to try, but there's a bunch of them in the book. So I want to talk about one more thing before I let you go. Do I have time? Okay, maybe a couple minutes. Okay, so here's something else I could do. I could give you this. This is a new sequence, and I could say, you give me a rule. Whoops. That's not what I want. Okay, and then I do this, and I say, what are the next three terms in this sequence?
9-1. Oh wait, hold on. 9 before.
What's the? This is
Wait.
this.
1,
It's E.
8. Oh, it's yeah.
So someone with a calculator handy.
Yeah, give me a second. Eight to 8.
4, 6.
Oh, something, maybe I wrote it down wrong. Yeah, 4, 6, right? 4, 6, round it off on your calculator because it ran out of spaces.
Yeah.
So check this out. What are these? This is definitely a sequence, and it's in order. These are the digits of E. Right? These are the digits of E. So the question is there a formula for this one?
Isn't it just E?
E is kind of the answer, right? More or less, if you put a decimal point in here. But can you come up with a formula that tells us the nth digit of E? Like, what if I want the 1000th digit of E? Is there any way to know what that is by rule? The answer is basically no, okay? I mean, yeah, we could probably write some kind of integral or something, but no, there's no simple rule for that. So sometimes we have a sequence, we can figure out what the next three terms are, but we can't really write an algebraic rule for finding it. So what you'd write is rule, right? The rule is digits of E. In other words, you can still describe the rule in words and tell people how to find the next digits, but it may not have a nice algebraic rule. And most of the sequences that we're going to consider do have nice algebraic rules, okay? But some don't. Here's another one. You're going to like this one. How about this one? I'm thinking you maybe have seen this one before. So I say, what are the next three terms and what's the rule?
Add the two previous terms.
That's beautiful. 8, 13, 21, 34, 55, more of them. Of course, the more I give you, the easier it is to sort of determine the rule. But I'm saying that coming up with an nth term formula here, hard. There is one, okay? But it's really hard to come up with. In fact, there was a guy that got his PhD for figuring that out. Do you know his name?
Pascal?
Close.
Isn't it just each one added like to the previous one?
It is. Guys,
Oh, Fibonacci.
Fibonacci. And he said, you know what? Maybe I can make a rule that looks like this. A sub n plus 1 is equal to, maybe I should say A sub n plus 2 is equal to A sub n plus 1 plus A sub n, where n is greater than or equal to 0. Yeah? Maybe greater than or equal to 1.
Yeah.
There's one other thing that we have to do for this rule, though. See, he said, add the two previous ones just like you did. That seems like a pretty cool rule. But I need one more piece of information. What is it?
What is A sub n?
Yes. A sub 1 has to be 1, and A sub 2 has to be 1. You got to know where to start, right?
Yeah, I know which one is which.
Because what if I gave you this? What if I gave you 2, 2, 1? You could still use the same rule, couldn't you? So the rule is still add the 2 previous ones, but we started somewhere different. Pretty cool, huh? I like this one. This is a really good one for the tester quiz. Write the rule. And you go, wow, if I gave you this, probably somewhere in your past, maybe kindergarten, I don't know, somewhere in your past, you probably saw Fibonacci before. That seems like a topic that maybe you saw in one of your grade school grades. But then this one, that's disguised a little bit, right? And it reminds you that for writing a rule like this, you got to tell me what's the rule and where do I start? This has a name. This is called a recursive definition. Of a sequence. Okay, this is a recursive definition, meaning that I get the next one by knowing something about what happened on the last one. In fact, I think we could go back, way back here to the other side, and we could take a look at this list of numbers. Can you write a recursive definition for that list of numbers?
Yeah.
How?
Don't know if you can actually.
How would I get the next one given the previous one?
+2.
Yeah, how about that? +2.
Yeah.
It's the previous one +2. And in this case, we have to tell you where to start. So where should we start?
2.
At 2. There's a recursive definition. Here's what we call an explicit definition. CIT. Explicit. There we go. Okay, what about this? What if I gave you the rule a sub n plus 1 equals a sub n plus 2 and a sub 1 equals 1? Could you write the sequence if I give you the rule?
Yeah.
Yeah.
What is it?
1, 3, 5, 7, 9.
Right on. And so you'd write odd numbers, right? That's another way you could write this down, odd numbers. And that'd be faster, maybe. Okay, could you give me an explicit rule for these?
Oh, is it just 2x or 2n minus 1?
Yep, 2n minus 1. Double it and take 1 away, and we get the odd numbers. Okay, so check it out. We got several ways that we can represent a sequence. We can represent a sequence as a list. We can represent a sequence with an explicit formula. We can represent a sequence with a recursive formula. And of course, we can represent a sequence with a picture, right, or a graph. And so if you wanted to make a graph, you could do something like this. You could say a sub, I don't know if I can do this, n minus 1, right, plus a sub n minus 2. Why is it kind of freaking out here? Because you defined a multiple ways. Oh boy. So one of the things that we're going to have to learn how to do is how am I going to represent these things in Desmos? And the answer is, well, explicit formulas work pretty good, but unfortunately, Desmos doesn't do recursion. So you can't say it's defined recursively, because Desmos doesn't know how to do that. And so every time, you know, if you want, you can go in there and say, hey, Desmos, when are you guys going to do recursion? That'd be a cool feature you could add to your program. And, you know, maybe they'll add it. Who knows? It's like one of the coolest programs in the world, but it doesn't do everything. Okay, so recursion is going to be hard. It's going to be a little bit hard for us to do in Desmos. It turns out that explicit formulas, no problem. So 2n minus 1, we say, I want to graph 1 to 10, and then I want to graph A of 1 to 10, and it says, no problem. There they are, right? There are the first 10 odd numbers. Okay. But recursion isn't going to work in Desmos. So if we want to do recursion, we're going to have to find another way. Fortunately for us, we just play with recursion a little bit, and maybe not as much as you might well, we don't have enough time, right, to really play with recursion. So we're going to introduce it, talk about it a little bit, and for the most part, not use it too much. So it's going to end up being that Desmos isn't too much of a limitation, the fact that it can't do it. Okay, so that's probably enough to get us started. That's enough to get us started. And nope, that's not enough. I want to do one more thing because I want to leave you with something to think about. Check out, here was our rule. I'm going to redefine this because I don't like doing all that typing. I'm going to say n is my list of numbers to 100. Okay, and then I'm going to graph NA of n. Okay, so there they are. Those are the odd numbers. Okay, but now I want to change the rule, and I want to change the rule to this. And then I want to ask you, what do you think is going on with these? In fact, what are the numbers? Can you list them explicitly? What's a sub 1?
1
Would
half.
be a half.
1/2. Right on. It's 1/2. So what's a sub 2?
1.
One.
No.
Be a third, right?
Yeah.
Or 2/3.
2/3. Yes.
2/3. Yeah. That's what I'm
2/3.
thinking.
Okay. What's a sub 3?
3/4.
3/4. What's a sub 4?
4/5.
4/5. Here it is right here. What's a sub 5?
5, 6.
5/6.
5/6. 6/7. 7/8. Right? What does it look like this sequence is doing?
It's getting closer to 1.
It looks like the values are getting closer and closer to 1. I told you there'd be a little calculus coming. Because if I were to say, what would happen as n gets bigger and bigger and bigger and bigger? I'm kind of hoping you're going to tell me that these values seem to be getting closer and closer and closer to
1.
1. Okay, so play with sequences a little bit as you get time. When you kind of finish up chapter 7, feel good about that. And then start taking a look at sequences, try a few homework problems, and then we're going to explore them some more and see how they turn out to be useful, okay, as we take a look at chapter 11. So that's all I got for you today. Any questions before we go? All right, I went really long today. Sorry about going so long. Just kind of got excited about all those warm-up problems, right? Okay, if you have questions or concerns, you can always come to office hours or send me an email. Otherwise, I will see you guys on Friday.
All right. See you then.
Yeah.
Okay,
See you then.
so long.